Explain the propagation of electrical impulses along a neuron, including the role of myelin. First, a quick review of synaptic transmission. One cell is going to secrete neurotransmitters which diffuse across the synaptic cleft, bind to ligand-gated sodium channels, and open, shown over here, allowing sodium to diffuse into the receiving cell. If enough of these neurotransmitters bind, what occurs is the second step. Closed voltage-gated sodium channels are going to open and allow even more sodium to diffuse in, as shown here. These are the voltage-gated sodium channels, and these are the ligand-gated sodium channels. The remainder of this presentation will be how the resulting action potential that has been triggered is going to be propagated down the length of the axon. To review, we need to know that a resting potential is negative 70 millivolts across the membrane. That means outside it's positive, inside it's negative. There's a lot of sodium on the outside and a lot of chloride on the inside, also a lot of potassium on the outside. This is the resting potential. Nerve impulses, all they are is action potentials propagated along the length of a neuron. When one action potential occurs, that is a change from negative 70 to positive 40 millivolts in one area, it depolarizes the adjacent area. And this basically just is repeated over and over down the length of the axon. This is achieved by local currents. That is, when sodium diffuses in, it also is going to diffuse laterally within the axon. Why does it not diffuse laterally backwards? I'll explain that in a moment. So after depolarization occurs, the interior is positive. So at positive 40 millivolts, potassium channels open, and potassium is going to diffuse out of the neuron, and that is going to repolarize the neuron. Later, what this means to adjacent areas is when sodium diffuses back this way, the charge is already positive. The voltage-gated sodium channels are already open, so no further sodium can diffuse in, no further action potentials can be achieved because the ion concentrations are the opposite of what they need to be. The sodium-potassium pump restores ion concentrations and the resting potential. It does that in the following way. So let's erase some of this right here. And so in the green, what we have is the opposite of a resting potential. Potassium is outside right now. It should be inside if we had a resting potential. Sodium is inside. It should be outside if we had a resting potential. So the sodium-potassium pump is the perfect pump to resolve this situation. It pumps 2 potassiums in. So these potassiums are going to get pumped back in, and it pumps 3 sodiums out at the same time, which restores the resting potential. And that's, again, why we can't have the action potential go backwards. In green, we call this situation when the ion concentrations are reversed the absolute refractory period. So myelin insulates the axon, and therefore it increases the speed of the impulse transmission. That's called saltatory conduction, and the impulse is going to jump from node to node. So what is the myelin? What are these nodes of Ranvier? So myelin is produced by Schwann cells, and if we cut, and you can see in yellow, this is a Schwann cell. It's wrapped around the axon, and if we took a cross section of this, well, you'd see this right over here. The interior, this is the axon, and the exterior, this is the Schwann cell. And basically, it just has these very thin and long extensions of its plasma membrane that wrap around the axon. The membrane consists of phospholipids, so those are fats, and that insulates the axon. There are regions where there's no myelin between the Schwann cells, shown right here. This is one of those regions. This is one of those regions. They're called nodes of Ranvier. And nodes of Ranvier are actually the only place on the axon that has sodium-potassium pumps, voltage-gated potassium and sodium channels, etc. So this is the only place where action potentials can occur. So the action potential, or the impulse, jumps from node to node, and therefore this increases the speed of transduction. This is your mark scheme, so you can check your work if you want to try practice answering this question. One last question, a really short one. Why is sweat a good coolant for the body? Is it A, arterioles that transfer water to sweat move closer to the skin's surface when it is hot? Well, arterioles are in a fixed position in capillary bed, so they cannot move. However, they will dilate. This answer kind of sounds right because they can dilate and move more water and therefore more heat to the surface of the skin, but it's not quite there. Is sweat non-polar? No, sweat is mostly water, and water is a polar molecule as shown over here. It has hydrogen bonds. Sweat contains minerals such as sodium chloride. That is a true statement, but containing sodium chloride is not going to cool the body in any way. B is the correct answer. Breaking hydrogen bonds between water molecules in sweat requires energy from the body in heat. So where does that energy come from, and why is that an effective way to cool the body? Well, because let's take a look at this graph over here. This amount of energy and this temperature, let's not get too wrapped up in the numbers. You can see there's a linear correlation. As you add heat to water when, say, the body is heating up, well, the water heats up as well. But at a certain point here, between here and here, you have to add a lot of energy to convert water to steam. So what happens as sweat is on the body is it slowly is going to evaporate. It's going to slowly evaporate, and that takes with it, the water takes with it any energy it has. So breaking hydrogen bonds takes a tremendous amount of energy. It takes 500 calories to evaporate 1 gram of water. This is the amount of energy required to break the hydrogen bonds in water. So 500 kilograms is a tremendous amount. As a comparison, just to go for 1 gram of water to change the temperature from 0 degrees to boiling, we're only going to need about, say, like 100 calories to increase it 100 degrees. But to break those hydrogen bonds, we have to add 500 calories. So those hydrogen bonds, when they're broken, they take all that energy, they evaporate and cool the body.